Hi everyone, my name is Hector Martin Peña Polastri, and I'm going to talk about the Drinfeld double of the Jordan plane, the Super Jordan plane, and their restricted versions. This is my talk for the Mathematical Congress of the Americas in 2021, and this talk is based in a joint work with Nicholas Andruszkiewicz. So let's go now. First, I'm going to introduce you some preliminaries about Jeter-Drinfeld models that are very essential tool for this work. So first, let H be a Hopf algebra. The category of Jeter-Drinfeld models over H, denoted by this notation here, consists on vector space B, such that B is a left H model with an action here, is an left H comodel with coaction delta, and we have a certain compatibility condition that is written here below. So this is a Jeter-Drinfeld model. And why this category is interesting is because of the following. The category of Jeter-Drinfeld models over a Hopf algebra is a Brady tensor category. That is, it is a tensor category, but it also has these linear maps, C and M, that can exchange tensors, can exchange N and M here, and is given by this formula using the action and the coaction. A Brady vector space, on the other hand, is just a pair of a vector space and a map C that satisfies this equation here, the Brady equation. Every Jeter-Drinfeld model is actually a Brady vector space with C, the categorical braiding here. A realization of a Brady vector space is actually to give the vector space B the structure of a Jeter-Drinfeld model over some Hopf algebra, such that C coincides with the categorical braiding of the category of Jeter-Drinfeld models. Given a vector space B, a Jeter-Drinfeld model B, we can define two Brady Hopf algebras related to it. One is the tensor algebra, that is the normal tensor algebra, but the braiding appears in the coproduct. The cotensor algebra, that here the braiding appears in the product. And by universal property of the tensor algebra, there is actually an algebra map, omega, that goes from the tensor algebra to the cotensor algebra. This map is actually a map of Brady Hopf algebras. So why is this interesting? Because it leads us to define the Nichols algebra. Nichols algebra are very important in the study of Hopf algebras. It's actually an invariant of them, and it is defined with this omega map. The Nichols algebra is actually the image of omega in the cotensor algebra. Every intermediate quotient B is called a pre-Nichols algebra, and intermediate inclusion is called a post-Nichols algebra. Well, this is very nice, but Nichols algebra appears to depend on a certain realization of a Brady vector space. That is not correct. The Nichols algebra only depends on the braiding, and I'll show you how with an alternative definition using quantum symmetrizers. The homogeneous components of these omega maps are called quantum symmetrizers, and they admit a description in terms of the braid group for n greater or equal to 2. In n1 or 0, it's actually the identity, so it doesn't matter at all. So given a Jeter-Drinfeld model, the braid group acts in the tensor n copies of V, and you exchange the component I with the I plus 1 using the braiding there. So with something like this in this formula. And okay, so why this action matters? Because you can describe the homogeneous component of omega as a sum over all the elements in the permutation groups of n ladders using this representation and using the Matsumoto section. That is actually a map that goes from the permutation group of n letters to the braid group of n elements, and it's not a group map, it's not an homomorphism, but it is very important and has very nice properties. So it is a set section, a very special set section there. So okay, given that, now we go to the main part of this talk, that is the restricted Jordan plane. First, we fix some notation. Let K be an algebraic closed field of characteristic P that is not 2, but it's of finite characteristic but not 2. And let gamma be the cyclic group of P elements with generator G, and we write this group multiplicatively. The Jordan plane is a very well-known quadratic algebra that is not a priori related with Lie theory, but we will do that here. It's an algebra presented by generators x and y, and this relation here. This algebra is actually very nice. It has a PVW basis, a very similar basis that the polynomial algebra in 2 elements is very nice overall, this algebra. And in characteristic 0, this is actually an Nichols algebra. Here is the connection with the theory. And characteristic 0 is the Nichols algebra of this specific 2-dimensional braided vector space with this braiding here. If you do the matrix of this, it seems very similar to a Jordan block. That's why the name Jordan plane comes. And in odd characteristic, the previous braided vector space, the Nichols algebra, is not the Jordan plane but a quotient of it called the restricted Jordan plane. This was shown by Silberslaut and Witherspoon in 2009. The restricted Jordan plane is just the quotient of the Jordan plane by the p powers of the generators here. It is finite dimensional. That is very nice because the Jordan plane is infinite dimensional. So we can use this to construct finite dimensional Hopf algebras, show some connection between the Jordan plane or the Jordan plane with Lie theory. Well, to do all of this, we need a realization of the previous braided vector space, and we realize this over the group algebra of gamma with this action and coaction that we write here explicitly. Well, as the restricted Jordan plane is a Nichols algebra, it is a braided Hopf algebra, but we want or need Hopf algebras, so by bosonization with the group algebra, using this realization here, we get a genuine Hopf algebra, H, here, built from the restricted Jordan plane. This H, we are going to compute the Drinfeld double of this H, and you will see what we obtain. It's actually very interesting. To construct the double of the Drinfeld double, we need the dual first. The dual is also a bosonization of a Nichols algebra of certain braided vector space that is here. It's very similar to the previous one, and the algebra function over gamma, that is the dual of the group algebra. And this actually is a quotient of a polynomial algebra in 1 dimension. It is, in fact, the restricted enveloping algebra of the Lie algebra of a 1-dimensional torus, and the P operation is the identity here. So, very nice overall. We have this presentation for the dual of H, opposite with opposite multiplication, because that's what we need to compute the double. So the dual of H opposite is the algebra generated by these 3 elements, U, B, and theta. With this relation, you here can see the same relation of the Jordan plane, some relation with the p powers, and this Lie-like relationship with zeta here. The double is then presented by these 6 generators, u, v, zeta, g, x, and y, with the relations of h, h-dual, and this relation that relates how you can exchange the elements of h and h-dual here. So very, very nice. And why this is nice? Because of this, exactly. The double is actually an abelian extension of the restricted enveloping algebra of SL2. So here we have a connection with Lie theory of with the restricted Jordan plane. So how we do this? Let R be the subalgebra of the double generated by G, X, and U. This is a normal commutative Hopf subalgebra, and there exists an exact sequence of Hopf algebra here that has at the left one algebra, this algebra R, and to the right the restricted enveloping algebra of SL2. As R is commutative and the restricted enveloping algebra of SL2 is co-commutative, this is actually an abelian extension. The R is actually also very nice because it's the Frobenius kernel of a certain algebraic group. Here GM is the field without the zero, and the operation is the multiplication, and GI is the field with the sum. This also is a local of algebra. We can compute with this extension the simple modulus of the double. Actually, the simple modulus are all simple modulus of the restricted enveloping algebra of SL2, as the Hopf ideal generated by R is an nilpotent ideal. In particular, there are p-isomorphic classes of simple modulus, and there is an explicit description of as quotient of permamodulus in the paper. You can see them there. Okay, so we did this all for the restricted Jordan plane, but with taking that as an inspiration, we can define something very similar for the Jordan plane, the classical algebra. How we do this? We define the whole algebra D tilde here as the algebra presented by generators u, v, zeta, g, x, and y with the same relation as the double, but we remove every relationship that has anything to do with the p power of the generator, like this. This is an infinite dimensional Hopf algebra, but it has finite Jelf-Kirill dimension. It has actually dimension 6, so it's very nice overall. It has a PVW basis. It's great. The Hopf algebra, it has a very big center also. This is very nice, very similar to what happens with Lie theory. The subalgebra C generated by the p powers of the generators, and this kind of p power of the generator zeta, that is zeta to the power to p minus zeta, is a central Hopf subalgebra, and we have this following result. There is an exact sequence of Hopf algebra that involves zeta and the double here. Recall the double is finite dimensional, zeta is a very big central Hopf subalgebra, and this is the double of the Jordan plane. Zeta is in fact the algebra function of a certain soluble algebraic group related with the 3×3 Heisenberg group. So very, very nice there. And we can summarize all this relationship between algebras in this following commutative diagram. Here we have SL2 to the right. Here, as you can see, the double of the Jordan plane is actually an abelian extension that from the enveloping algebra of SL2 and the algebra function of a certain algebraic group. Here below we have the finite dimensional version, the Frobenius kernel R, the restricted enveloping algebra, and the double of H is a kind of a restricted version of the double of the Jordan plane. Here at the up left part we have the Frobenius map, and every row and column here is actually an exact sequence of algebras. So very nice. We also computed in a following paper we're going to show, but we also did this. We computed the simple models, finite dimensional simple models of the double of the Jordan plane, and they are the same as the SL2 models. So the same result that we have here for the double of the resistor Jordan plane, it holds for the double of the Jordan plane. The proof is a bit more complicated, but it also can be proved. Well, what else we did? We did the same thing for the Super Jordan plane. I'm not going to explain this in all the detail for the Super Jordan plane because of time. We have very little time left. But essentially, in a work, Andruszkiewicz and John Hagenberger introduced another indecomposable Brady vector space of dimension 2, that is this one. In characteristic 0, the Nichols algebra has Drinfeld dimension 2, and it's called the Super Jordan plane. It actually has the Jordan plane as a subalgebra. It's very nice. The adjective super is not very justified in their paper, but with the construction we did, it is actually justified, as we see that this algebra actually has relation with the theory of super Lie algebras and Superhof algebras in general. You will see. In characteristic P, the same as before, the Nichols algebra of this Brady vector space has finite dimension, is a quotient of the Super Jordan plane, and we call it the restricted Super Jordan plane. So very similar to what happens with the Jordan plane. In another paper with Nicolas, we carried out the same problem for the Super Jordan plane and obtained the following result that is very similar. Here all the algebras involved are actually Hopf superalgebras, not Hopf algebras. So you have a relation with the superwork here. Here D is kind of a double of the Super Jordan plane, but it's a Hopf superalgebra, so it's not a different double of a Bosonization. The D tilde here is the double of the Super Jordan plane. And to the right we have the enveloping and restricted enveloping algebras of the Super Lie algebra, OSP12. And I recall you this is a classical Super Lie algebra. It's the smallest simple Super Lie algebra that has no trivial odd part. So very nice. And to the left here we have a commutative Hopf superalgebra, that is the algebra functions of a superalgebraic group. Here the algebraic groups that appears, this G and B are P tilde, are different than the one that appears before, that why we put the tilde there. This justifies in some sense the adjective super given Super Jordan plane. And we also compute the simple models. They are all the same that the OSP, the restricted Lie algebra, restricted enveloping of algebra of SP12. They are the same. So very analogous results that we got for the Jordan plane. We got the same ones for the Super Jordan plane. Okay, this is all what I wanted to tell. We are working to investigate a very similar scheme for other algebras, with other algebras related to Brady vector spaces, for example, trigonal algebras and such. So we probably show them when we finish that work. So thank you very much for listening. I hope you enjoy the rest of the talks of MCA. See you. Here I forgot to show you some reference here for the talk. So I added this later as an edit.